I said this 100 times, president of the OLLI Advisory Board. Sorry if you have to keep hearing it. We're trying to get consistent information across all of the classes. And so people like Robert, who sign up for all the classes, I apologize. Just a reminder that winter registration opened Monday morning, and as of yesterday, we had over 251 people who had signed up. So I urge you to sign up for courses for a course that you're really interested in order to make the cut. Today, on behalf of our director, Norma Clippard, and the OLLI Advisory Board, there's Norma just came in the room, in case you don't know who she is. Thank you. Thank you for a wonderful curriculum. And also I'd like to thank the Vanderbilt University students under the leadership of Karen Burnett, who have helped us with the IT support this term. And as well, we cannot be more appreciative for the classroom assistants and all of their efforts and the work. For this class, it has been Lisa Otten and John and Arlene Yeager. Under the leadership of Jan Goddard, who is the chair of classroom assistants, and Pat Holdridge is her assistant chair. And what happens at classroom assistant orientation before each term, Jan and Pat go over all of the things that they need to be aware of and some lessons learned. We're going to have a lessons learned meeting this Friday, lessons learned from the fall term, so to tweak it and try to make it better and better for everybody. I would also like to bring this course to a close and sincerely thank David Weintraub. Thank you for conveying just a tiny part of your vast knowledge about Mars and expanding our thoughts about whether or not we should visit that planet. Thank you.
Can't believe you came back again. So this is it. Got a lot to cover today. I may rush through it, and then we'll have lots of time at the end, or I may not finish it. We'll find out. But let me remind you where we've been. We started by talking about how close humans are to setting foot on Mars and actually colonizing Mars. And we talked about some of the ethical and moral issues associated with that, because we, at the moment, can't get those astronauts home again. Minor details. Then we talked about how astronomers in the 18th and 19th centuries made a number of discoveries about Mars in which convinced them that Mars was an Earth-like planet. One of the big discoveries they made was that they found water on Mars. That convinced them that Mars could have life. They then, of course, discovered life on Mars and discovered there were Martians and re-engineering the planet in a major way. All of that, of course, was wrong. We know that was wrong. But they created an idea about Mars in which Mars has Martians. In the 20th century, we had science fiction novels, we had movies, we had every possible version of Martians in our culture, so that we have become very comfortable with the idea that Mars probably is inhabited, even though those were science fiction stories and Hollywood movies. In the 20th century, astronomers first looked for, discovered, and then found they were wrong about finding chlorophyll on Mars. They looked for and proved that lichens exist on Mars, and then that was shown to be wrong. They found moss on Mars, and then that was shown to be wrong. They found algae on Mars. That was shown to be wrong. And by the 1960s, by the dawn of the space age, we had become convinced that Mars probably was sterile, because we hadn't found anything. What we did learn in the space age is that Mars has a lot of water. And once upon a time, Mars was warm and wet and was an Earth-like planet. So we've gone back to where we started in thinking that the possibility that Mars could once have been inhabited is very, very real. And therefore, the possibility that Mars might still be inhabited is plausible. We then looked at some of the more recent measurements, the Viking measurements we looked at last time, the Viking missions in the 1970s. The Viking scientists did 4 different biology experiments. Almost everybody is convinced that those experiments show that Mars does not have life. except there are folks who are not convinced. And the proof that the Viking measurements found that there are absolutely no organic molecules, carbon, hydrogen-containing molecules on Mars, has now been shown to be wrong. So Mars could have life. Then we looked at the meteorite that was discovered in Antarctica in 1984, that in 1996 exploded into the popular world with evidence that that meteorite had evidence for ancient life on Mars, including fossil nanobacteria, which nobody believes anymore, except it might be right. So that's where we are. I want to take you down one more rabbit hole, and that rabbit hole has to do with methane. So all of today is about a molecule. And the dawn of the methane era on Mars began in 1969, when we launched the Mariner 7 spacecraft, which did not go into orbit around Mars. We did not yet have the ability to launch a spacecraft and put it in orbit around another planet. This just flew past Mars. It flew past Mars fast enough that it took 126 grainy images of Mars, and that was almost everything it was able to do. But it proved we could do this. But it did have an instrument on board that was able to measure spectra of Mars. It was able to look at the atmosphere and try to study the atmosphere to figure out what the atmosphere was made of. The Mariner 7 mission proved that the Martian atmosphere is almost entirely carbon dioxide and that the Martian atmosphere is very thin. But the Mariner 7 team also claimed to have detected methane. This guy, George Pimentel, was the principal investigator of the infrared spectrometer team on the Mariner 7 mission. George Pimentel is a giant of 20th century chemistry. There's a building on the Berkeley campus named for him. There's a statue outside that building named for him. He didn't make many mistakes. You know where this is going. Okay? He said at a press conference, I want to point out the date here, August 7th, 1969, and let's go back to the moment when this spacecraft arrived at Mars, August 5th. NASA held a press conference 2 days after the mission arrived because you are the taxpayers, you paid for this mission, NASA wants lots of popular acclaim for what they're doing. Nothing has changed since 1969. This is a month, less than a month after we landed on the moon. NASA's having a good ride at the moment, and NASA wants you to know about what you have paid for and what you have discovered on Mars. So they host this press conference. George Pimentel says, we are confident that we have detected gaseous methane and gaseous ammonia between approximately 61 degrees north, 61 degrees and 76 degrees south latitudes on Mars. So they know a specific region on Mars toward the South Pole where they have detected methane and ammonia in the atmosphere. Headlines. New York Times, 2 gases associated with life found on Mars near polar cap. Los Angeles Times, Mariner hints life on Mars. All around the world, Mariner 7 has discovered substantial evidence that there's life on Mars. George Pimentel's #2 person on this project team, Kenneth Kerr, and I have tried so hard to find a picture of this guy, and it doesn't exist, right? But Kenneth Kerr chimed in at the press conference, I have no clue as to the origin of these gases. Kenneth Kerr should have stopped right there, okay? But he didn't. He continued, he said, and I believe they are, but if these readings are true, and I believe they are, we have to face the possibility that they could be of biological origin. Bingo, we have found evidence for life on Mars in the form of methane. So what is the big deal with methane? Here's the big deal with methane. Here's your friendly cow. The cow eats some grass. The grass goes into one of the many stomachs of this cow. Some bacteria digest and ferment the grass. Inside the cow's stomach, that produces hydrogen gas and carbon dioxide gas, and then some other bacteria known as methanogens take the hydrogen and the CO2 and turn it into methane. And then the methane comes out of the cow at both ends. Right? This is a major production source of methane. On the Earth, here's where we get our methane. About 10% of it comes from bacteria in the mud in rice paddies. About 20% of it comes from ruminant livestock, goats, sheep, cows, llama. 15% come from the bacteria in the guts of termites. 30% of it comes from landfills and wetlands and wastewater treatment facilities, which are taking biological material, biological waste, and processing it. And 25% of it comes from burning and producing fossil fuels, which is digging coal and shale and oil out of the ground and using it. And all of those materials came from living things a long time ago. 100% of the methane in the Earth's atmosphere comes from life. There's a number up here which you don't have to memorize, but there it is. The amount of methane in the Earth's atmosphere is 1,800 parts per billion. If I had 1 billion molecules from the air, 1,800 of them would be methane molecules. That doesn't sound like a lot, but it's actually a huge amount of methane. It is such an overabundance of methane that if I could take a telescope and go to the other side of the Milky Way galaxy, I'm going to go 100,000 light years from Earth. And if I had the technology to prove there's a planet Earth orbiting the sun, and I could use my telescope to isolate the light from the Earth, I could detect this methane without any problem. And because the Earth's atmosphere has both methane and oxygen and ozone in it, I would know without any doubt that there is life on Earth. Because methane and oxygen don't coexist. They can't exist in the same atmosphere unless something is actively manufacturing one of them. And in fact, in the Earth's atmosphere, life is actively manufacturing both of them. I could prove life exists on Earth by pointing a telescope at the Earth and detecting the methane. Methane is a great tool to try to look and discover whether life exists on a distant planet. The methane in the Earth's atmosphere is way out of its natural abundance, which should be 0. There are some other numbers up here. In the Earth's atmosphere, as we pump the methane into the Earth's atmosphere, it gets rapidly destroyed. Ultraviolet light from the sun helps destroy it. Other processes in the atmosphere help destroy it. 12 years. That's the half-life for the methane in the Earth's atmosphere. Within 36 years, virtually all the methane would be gone if we didn't produce more of it. The Earth's atmosphere should have no methane in it, but it has lots. Life. Mars's atmosphere has a longer lifetime for the survival of methane gas in the atmosphere, 300 years. But Mars is 4.5 billion years old. If Mars was born with lots of methane, then 1,000 years after Mars was born, the methane's gone. If Mars has methane today, something is producing it. Now, Mars does not have an oxygen-rich atmosphere, but it has a carbon dioxide-rich atmosphere, CO2. CO2 is an oxygen-rich molecule, and methane cannot coexist in an atmosphere with that overabundance of oxygen-rich molecules. If methane exists in Mars's atmosphere, something is actively creating it. And that something could be creatures. This is why astronomers latched onto methane as something to be looking for in the Martian atmosphere. And Mariner 7 found methane until they didn't. Okay? A month later, September 11th, they held another news conference. At the news conference, George Pimentel said the spectral features previously attributed to methane and ammonia were, in fact, caused by frozen carbon dioxide, dry ice. The new discovery removed one of the final hopes scientists held of finding life on the planet. He really shouldn't have said that. The fact that carbon dioxide can mimic the behavior of methane and ammonia was just a cruel coincidence. It was not a cruel coincidence. It was science done badly. They should not have had a press conference 2 days after the spacecraft arrived at Mars. They should have gone back into their labs and done their homework, and they would have discovered that they had detected carbon dioxide on Mars, not ammonia and methane. So they were embarrassed. Putting scientists in front of microphones at press conferences is normally a bad idea, because we're not trained to do this. And this is a good example of that. The Wall Street Journal reported that this is a perfect example of the hazards of quick conclusions. Yeah, it is. So the final Mariner 7 result, which they published several years later, was that they had not detected methane. They said they had detected less than 3 parts per billion, and in the language of how good a signal and how much noise was in the data, what that actually means is that they were confident at a 99.7% confidence level that there are less than 5,600 methane molecules per billion molecules in Mars's atmosphere. So this little phrase, parts per billion, you're going to start to see on lots of slides as ppb. When you see ppb, it's parts per billion. Their non-detection was less than 5,600. Now that's a lot of methane since the Earth has 1/3 of that. So it's not much of an upper limit, but that's what they found, an upper limit to the amount of methane. The search for methane continued. In 1969, NASA launched Mariner 9. Mariner 9 was the first interplanetary spacecraft to actually go into orbit around another planet. So it was inserted into Mars orbit November 13th, 1971. That shouldn't say 1969. Oh, well. That should say 1971. This goes into Mars orbit, and I have no great pictures to show you of what they found because they didn't find anything. They didn't have a press conference. They didn't embarrass themselves. They did search for methane. It took them 5 years before they published their results in a scientific journal. And when they did, they said the amount of methane in Mars's atmosphere is less than 30 parts per billion. So the upper limit has dropped from 5,600 parts per billion to 30. But that doesn't mean there's no methane. It just means there's less than 30 parts per billion. The search for methane took a break for about 20 years. The next time methane shows up in our story is 1997, when this team of folks, led by Vladimir Krasnopolsky and Mike Mumma of Goddard Space Flight Center in Maryland, used a telescope at KITT Peak. This is KITT Peak National Observatory in Arizona. This big guy up here, that's the 4-meter telescope. They won't let me use it anymore because I proved that it jiggles a little bit too much, so they didn't like me there. All right, anyway, there's your 4-meter telescope. Okay? And they used it in 1988 to search for methane. They didn't publish their results until 1997. I don't know why. They had other things to do. They put it in a drawer. They finally got back to it and worked on their data. They used a particular technique to try to identify the methane because there's a problem in looking for methane with a telescope on the Earth. And the problem is the telescope's on the Earth. If you have your Mariner spacecraft that has gone to Mars, you are not looking through the Earth's atmosphere in order to look at Mars. But this telescope in Arizona has to look through all of this muck above it in order to look at Mars. So light from the sun travels through interplanetary space to Mars. It penetrates the Mars atmosphere, bounces off the surface of Mars, goes through Mars's atmosphere again, goes across another 45 million miles of empty space, and then goes through the Earth's atmosphere to our telescope. So the signal we measure in our telescopes on Earth when we're looking at Mars is a convolution or a combination of what the sun is doing to the light, what Mars is doing to the light, and what the Earth's atmosphere is doing to the light. And they've got to tease all that apart. Amazingly, they found methane. Now, they did tell us, I'll tell you what these images are in a moment, they did tell us that in their measurements, the amount of methane in the Earth's atmosphere above the telescope that they're looking through is about 2,000 parts per billion. But they put an error bar on that, 2,000 plus or minus 1,000, which means it might be 0 or it might be 5,000. But we actually know the average amount is about 1,800. So that's a good number, 2,000. In the top image, this is a close-up of a little tiny bit of the spectrum of Mars, where they have made corrections for the sun's influence and Earth's influence. And this deep dip, you're going across wavelengths from left to right. And this deep dip, which is marked with the circle with the cross in the middle, that's a symbol for the Earth. This feature is due to the methane in the Earth's atmosphere. If the Earth had no methane, then the line across this profile would just go straight across. But methane in the Earth's atmosphere absorbs some of the light and creates this dip. So this is called transmittance. This is how much light at a particular wavelength gets through the atmosphere, and where the methane is concerned, it absorbs 90% of it. Only about 10% gets through. Where there's no methane, you have all the light. So we know how to detect methane in the Earth's atmosphere. What about Mars? At the time of their observations, the Earth and Mars are both orbiting the Sun, but they're orbiting at different speeds. As a result, Mars's spectral lines, the feature due to methane, is red-shifted or blue-shifted with respect to the same lines in the Earth's atmosphere. That means that this dip due to methane in the Earth's atmosphere would be at exactly the same place if Mars and Earth were both sitting still. But because they're moving away from each other or toward each other, depending on the situation, the Mars line is shifted away from where the Earth's is. So at this particular time, Mars was moving away from the Earth, and that shifted the Mars line to right here. So that little symbol is for Mars, and they claim that that little dip is due to methane. The bottom figure is a close-up of this little dip, but they've flipped all the data upside down. So rather than the dip representing how much methane Mars has removed, they flipped it upside down so the hash marks represent how much methane Mars would be contributing. Either way, you get the same answer. This feature is supposed to be caused by the methane in Mars's atmosphere. Now, if you look at the top image, you'd say, I'm not sure, it's kind of noisy. And if you look at the bottom feature, you'd say, I don't know, it's kind of noisy because this thing right here at about 0.03 isn't very different from this thing. This thing at 0.015 isn't very different, but they're not crediting that to anything. But they say that's methane. They gave it a number, 70 plus or minus 50 parts per billion. Now, the Mariner folks had already said less than 30. And they're saying more than 30. But they're not really saying more than 30. They're saying 70 plus or minus 50. What does an error bar mean? Error bars are important. 70 plus or minus 50 means that it might be 20. It might be 120. There's about a 65% chance that it's between 20 and 120. There's a 95% chance that it's between 0 and 107. There's a 99.7% chance that the right answer is between 0 and 220. That's called 3 sigma, add 3 times the error to the number. They have not detected methane. They have what the Mariner folks had. They have an upper limit how much methane is there, and that's 220 parts per billion, which is almost 10 times as much methane as an upper limit that the Mariner 9 folks had found, which means they haven't contributed anything to our knowledge about methane. Except they marketed this number as a detection because the signal, 70, I guess, is bigger than the noise of 50. So they said, we've detected methane on Mars. They then leveraged this to get more time on more telescopes. That's the game astronomers play. Yes?
Are there any proof that there's any kind of clouds, dust clouds or anything like that between here and Mars? Because radio astronomers, people have picked up fluoride and all sorts of crazy organic things in dust clouds.
Is there any evidence of dust clouds in between the Earth and Mars? Because radio astronomers can detect all sorts of molecules in space, in interstellar space, in what are called giant molecular clouds. Giant molecular clouds do exist in the galaxy, in other galaxies as well. They don't exist within the solar system. So there's nothing in between the Earth and Mars. There are a few asteroids, rocks, but there's no dust. There's nothing in between the Earth and Mars could possibly cause this. This is either signal that is the result of something in Mars's atmosphere, or signal that's the result of something misunderstood or not understood in the Earth's atmosphere, or mis or not understood in the Sun's atmosphere, or it's noise. But it's not something in between the Earth and Mars. All right. They marketed this to get more time on more telescopes. Interestingly, I'm going to show you their names again. 2 of the biggest players in the search for methane are Krasnopolsky and Mike Mumma, but this is the last time they talked to each other, at least publicly. They have both continued to work on the methane in Mars's atmosphere problem completely independently. They are competing with each other and have been for the last 20 years. The next player in the Mars methane game was this thing, ISO, the Infrared Space Observatory. ISO was launched by the European Space Agency. It was put into Earth orbit. Its job was to study the universe at infrared wavelengths, which is hard to do from telescopes on the ground. In 1997, ISO did a project to try to study the methane in Mars's atmosphere. And these are their data. The x-axis is wavelength, so this is infrared wavelengths of light. The vertical axis is just how much light you're getting. The data is the really jaggedy profile that goes through the plot. And then there are two lines, smooth black lines, that are fit to the data. Those are model atmospheres, as the planetary astronomers would call them. And what we're looking for are where these two lines are drawn, at 3.27 and 3.314 approximately. If Mars has methane in the atmosphere, we should see drops, dips, in the profiles at these wavelengths. And we don't. The top line in this profile, there are actually three. The top line is a model atmosphere of Mars that has zero methane in it. And these other features are well fit because those are features from water and carbon dioxide. There's no methane there. The bottom one would be what Mars would look like if there was 50 parts per billion methane. Doesn't fit, doesn't fit. And the bottom would be 500 parts per billion. Doesn't fit, doesn't fit. They concluded that the tentative detection of methane, this was really nice, the 70 plus or minus 50 that Krasnopolsky and Mumma reported, they're describing that as a tentative detection. The tentative detection reported by Krasnopolsky et al. Is indeed marginal at best. That was a very nice way to dismiss the previous folks' work. Krasnopolsky's back. It's January 1999. He's used those KITT peak measurements from 1988 to get data, to get time on this telescope. It's known as the Canada-France-Hawaii telescope. It's on Mauna Kea in Hawaii. He was working with one guy who was at the University of Hawaii, which is how he got access to it, and one guy from France, which was also how he got access to that telescope. And in January 1999, he used the telescope to search for methane on Mars. It took him 5 years to publish the data this time, but amazingly, he found methane again. Okay? In this case, Earth and Mars are moving toward each other. Mars is moving toward Mars at 11 kilometers per second. So again, the methane lines in the Earth's atmosphere and Mars's atmosphere are shifted away from each other. That's the trick that should allow him to detect this. Astronomers use this all the time, and it works well. So methane in the Earth's atmosphere should show up where this line is, about 2979-ish. And methane in Mars's atmosphere shows up where it says Mars CH4 on the right side of the plot. And this tiny little dip there apparently is due to methane. That dip apparently is noise, and that dip is noise, and that dip is noise. And there's a real pattern to the dips here which suggests some systematic problem in the data. But he reports that as methane. You detect some skepticism from me here? This data down here on the bottom, that's a blow-up of that little region of the plot to show you the data with error bars and that deep dip right at 2979.2. Well, that apparently is the methane. And this time, Krasnopolsky and his colleagues report they had detected methane at a level of 10 plus or minus 3 parts per billion. It's not 70, but they've detected it. It's 10. Now, 10 is below the limit that Mariner 9 suggested. All Mariner 9 could say is less than 30. So this is consistent with the Mariner 9 measurements, 10 plus or minus 3. They then made the claim that we have not found any significant abiogenic source of methane. We haven't found any possible source of methane that is not biology. Therefore, methanogenesis by living subterranean organisms is a plausible explanation for this discovery. So they have two things in this little statement. One, they're claiming that they've detected life on Mars. And two, they're claiming this is actually a discovery and not noise. But it's 10 plus or minus 3. This is their 2004 results. At the same time, also in 2003, 2004, the European Space Agency inserted the Mars Express spacecraft into orbit around Mars, and it's still actively in orbit making observations of Mars. And Mars Express, amazingly, also detected methane, and also detected methane at the level of 10 parts per billion. Now, their noise level was higher, 10 plus or minus 5 instead of 10 plus or minus 3. They thought the methane got as high as 30 parts per billion and as low as 0. Again, we have this is wave number, not wavelength, because that's what chemists like. This radiance just is how bright, how much light you're getting, and the data is in here somewhere, and there are lines fit to the data. It says the deep line at 3012, right here, that's due to sunlight. The lines at 3000, 3.5, so that guy, and at 3022, that guy, and at 3026, that guy, those are all due to water vapor. And what we're looking for is at 3018. So we're looking for this thing right there, right? That thing right there. So the data is hiding in there, and there are also 2 model fits to the data. One model fit is, well, I thought it was there. The middle line is the data. The upper lower lines indicate the noise level in the data. All right. If you look in there, you can blow this up as much as you want. You can't distinguish between anything there. The question is that really a detection? And they claim it is at 10 plus or minus 5, which means it's not a strong detection. But now we have 2 different teams, one with a spacecraft around Mars, one with a telescope on Earth, in 2004, who are both reporting that they detected methane at the level of 10 parts per billion on Mars. The Mars Express people were a little more cautious in saying, we want to stress that the detection of methane does not imply the presence of life on Mars, now or in the past. It is one possibility, but other sources are equally plausible. So we have a disagreement as to what is actually the possible source of the methane. And then we have Mike Mumma, who gets back into the game again. He is using another telescope on Mauna Kea in Hawaii. This is Mauna Loa in the background, by the way. And the clouds in Hawaii come up to about 7,000 to 8,000 feet. So when you're at the telescope, you're usually above the cloud deck, which is nice. Again, this is the summit. This is Mauna Loa in the background. So Mike Mumma is using this telescope, the infrared telescope facility on Mauna Kea. NASA built this telescope in support of planetary missions. That's why it's a NASA telescope. NASA studies planets. So if you want to use this telescope, you're supposed to study planets, and that's what they were doing. So he did this January of 2006. He reported that he has detected 20 to 60 parts per billion methane in the north. It's lower in the south, but it was more than 250 parts per billion at the equator. 250 at the equator. Now, the Mariner folks had said less than 30. And Krasnopolsky is saying 10 plus or minus 3. And Mars Express is saying 10 plus or minus 5. And Mike Mumma is saying it's as high as 250 parts per billion at the equator. That's a lot of methane. So he's made a number of claims. One is that the amount of methane is not even throughout the atmosphere of the planet. It varies with latitude going north and south. The abundance can be very, very high. He had to come up with a reason why he's seeing so much methane and others are not. And his claim is that some process underground is releasing big bubbles of methane. Mars is burping methane into the atmosphere, and the big burp occurred at the equator. This is what he called a localized release of methane, and then he said, these measurements, these numbers cannot be waved away as a measurement error. Those are his words, not mine. So it's 2006. You cannot wave away these results as a measurement error. In 2009, he finally actually published his data. From 2004 to 2008, Mumma kept showing up at conferences and presenting his data, but not actually publishing the results in a refereed journal, which is what you're supposed to do. When he finally does, he publishes it in Science magazine. It's a big splash. This is his map of Mars. The different colors tell you how much methane he's seeing, where the purple, I guess that's purple is, you're not seeing much, if any. It's down around 5 to 8. But the red is huge. It's 30. It's not 250. It's not 60. Those numbers that previously could not be waved away as a measurement error don't exist anymore. It's the same data. He hasn't collected more data. This is exactly the same data, which is being reanalyzed, and you can see he has these maps of Mars in which there are variations with latitude, and these regions where it's super high tend to be where the volcanoes are. And he claims that the methane comes from 2 local sources on the planet, and it bubbles out, and then it disperses, and then it becomes undetectable because it's dispersed widely. The strongest signal in this 2009 paper was 29 plus or minus 9. He also reported some very low numbers. Has he detected methane on Mars? He would say yes. Krasnopolsky gets back into the game again. In February of 2006, both Krasnopolsky and Mumma used the exact same telescope in Hawaii, the IRTF, using the exact same detectors 3 weeks apart to make exactly the same measurements. And amazingly, Mumma did not detect methane in the atmosphere of Mars in late January of 2006, which is why he said in that paper he detected it in 2004, but it had dispersed and become undetectable in 2006. But 3 weeks after Mike Mumma could not find methane in the atmosphere of Mars, Krasnopolsky used the same telescope and he found it, I guess. When he first looked at this data, and the x-axis is latitude, so you're going from the southern hemisphere of Mars at minus 80 up to the equator and then into the northern hemisphere. And the different symbols represent different longitudes on Mars. So 67 degrees, the plus symbols represents how much methane you see at a particular longitude on Mars. And you can see it goes up near the equator and then down again. And at 72 degrees longitude, it goes up near the equator and down again. And at 89 degrees, it's not as much, but maybe. In 2007, he reported these measurements in a paper and said, didn't detect any methane. But in 2012, he had revisited the data. He had better computer models to account for what the Earth's atmosphere is doing and what Mars's atmosphere is doing. And in 2012, he said, actually, I did detect methane in this data at a level of 10 to 20 parts per billion, and that's what you see there. That's his detection of methane. And again, if he really detected it at 10 to 20 parts per billion, this was 3 weeks after Mike Mumma had not detected any methane, which was 2 years after Mike Mumma had detected 250 parts per billion methane, which 3 years later he reported as 29 parts per billion methane. Doing this work with a telescope on Earth is exceedingly difficult because of the problems we've discussed. Looking through the Earth's atmosphere, which has 1,800 parts per billion methane on average, it means the methane in the Earth's atmosphere is swamping your signal. The Mars water vapor, the Earth water vapor, the Mars CO2, the Earth CO2, puts all these other signals into your data, which you have to account for. Doing this work is very, very difficult. That being said, in 2009, Krasnopolsky made the same measurements with the same telescope he'd used in 2006. And again, this is latitude going from south to north. 0 is no methane. This is parts per billion of methane. These are data points with error bars, and all the error bars, except for maybe that one, are consistent with no methane. And he reports in 2009 that he has not detected any methane on Mars. So the methane comes and the methane goes. The Mars Global Surveyor was launched in 1996. The Global Surveyor was not designed with the ability to detect methane, but a number of folks on the Mars Global Surveyor instrument team came up with a scheme that they thought would enable them to detect methane. These are their maps of methane on Mars. A lot of figures here. The left-hand column is Mars year 2425. Mars's year is 2 Earth years approximately. The next column is the next Mars year called Mars 2526, and the third column is the third Mars year. These run from about 1998 to about 2004 Earth time. The top panel is at longitude 180 degrees, so these are, again, different longitudes on Mars. And the top left, where there's a little bit of red, you're looking at the region where the Martian volcanoes are. The Tharsis Bulge region with Olympus Mons. That's where they see the most methane. And they see methane. And again, we have a color bar for scale. The deep blue purples are not much methane, 0 to 16. And at certain longitudes, they don't see any. But at other longitudes, we got green and yellow and even red. We have methane at the level of 30, 40, 50, 60, 80 parts per billion. They said they detected that methane changes with the seasons, and in the autumn, they detected in the 3 different years, one year 33 plus or 9 parts per billion methane, the next Martian year 18 plus or minus 7, the next year 30 plus or minus 8. These are marginal, but 3 in a row, it's looking pretty good. Okay? In the winter, the methane is less, 6 plus or minus 2, 5 plus or minus 2, 5 plus or minus 1, and the methane is more abundant at higher elevations and near the volcanic regions. This is starting to look interesting. You have seasonal variations. You have variations with topography on Mars. Maybe there really are source regions. This is what they reported in 2010 using the data from 1998 to 2004. They do report in that paper that they had used a particular technique to cull their data, to remove the data from orbits of the spacecraft where they thought the data was bad. Anytime you cull your data, you're going where you shouldn't go. In 2015, the exact same team of scientists reported again that they kind of goofed. Okay? So this is a very different kind of plot. This is brightness, temperature, but that's how much signal you get from a methane line, and this is supposed to be one of the methane lines. So the dashed line is what they measured. That's the spectrometer, the thermal emission spectrometer tests on this spacecraft. So this is what they measure, and right where the line, the arrow is, that's where the methane should be. And if there's methane, they should be able to use their atmospheric model to show it's there. And there are 2 lines in here that you cannot distinguish. One is what they call the best fit, which is 33 parts per billion methane. And the other model Mars atmosphere fit to the data is exactly 0 parts per billion methane, and there's no difference. You cannot tell the difference. They concluded that the precision needed to definitely identify the presence of methane is extremely hard to reach, if even impossible at present, and they retracted these beautiful, beautiful maps of methane in the Mars atmosphere. They said, actually, we can't do that. And that was from a spacecraft in orbit around Mars. But the spacecraft was not designed to detect it. All right. Geronimo Villanueva led a large team of astronomers over a 4-year period, 2006 to 2010, to try to detect methane in the Martian atmosphere from 3 different telescopes. One of them is the IRTF that we're now familiar with. One is known as the VLT, the Very Large Telescope. Astronomers sometimes are not so tricky with their acronyms. So we have the Very Large Telescope. It's on a mountain in Chile. This is one of them. The VLT is actually 4 different 8-meter telescopes. It's a big telescope, 25 feet across. And there are 4 of them operating in tandem to make your measurements. This is the Milky Way in the southern hemisphere. The other telescope they used was one of the 2 10-meter Keck telescopes on Mauna Kea. So here we have the twin Keck telescopes. Each one of these has a 10-meter, 35, 36-foot diameter mirror inside it. These mirrors, by the way, when you get mirrors that big, they're not one piece of glass anymore. They're lots and lots of little pieces of glass that computers use to kind of keep them working together. It's called a segmented mirror, and that's how astronomers are building big telescopes. And with the KEK, there is a system called a laser guide system where you use lasers, you bounce the lasers off of sodium atoms in the atmosphere, and you watch the response from the sodium atoms, and that tells you how the atmosphere is moving around, and you can track that moving around and then unmove your data, so you get very, very precise data. This is called adaptive optics, and virtually every telescope in the world now tries to use adaptive optics. Here's their data. This is hard to look at, so let me try to take you through it. This is from the IRTF in January 2006. The top line is the observed data. Okay? Observed. Telluric means you're seeing the Earth signal plus the Mars signal plus the solar signal. And there are clearly some big dips in the signal. The next one, which is labeled B, they have removed the signal of the Earth's atmosphere from the data. And most of those big dips go away. Those big dips were caused by stuff in the Earth's atmosphere. So what is left is caused either by Mars or the sun. And there's lots of stuff there. The drop below the line means there's some molecule either in the sun's atmosphere or Mars's atmosphere that's removing a little bit of light. The next line, they've removed the contribution of the sun. We know what the sun looks like. You can remove the contribution of the sun. And what's left is Mars. So the squiggly black box thing, that's the data that is just Mars. And they have applied a model to this, the blue line, and that model is Mars's atmosphere with the known amount of water and carbon dioxide in Mars's atmosphere, and it's a beautiful fit. I mean, it really is a nice fit to the data. All of the lumps there, all of the dips are due to CO2 and water in Mars's atmosphere. In the next line, they have removed the signal of CO2 and water in Mars's atmosphere, so what's left would be created by something in Mars's atmosphere that's not water and not CO2 and has nothing to do with the Earth and has nothing to do with the sun. And there's a lot of noise, but you can see this dip here in the smooth line. Right? The smooth line is not the data. The smooth line is the model. And that dip is what the spectrum would look like if there's methane. There's no methane. And Villanueva reports there's no methane. In his observations from the IRTF, there's no methane. In his observations from the VLT, there's no methane. In the observations from the KEK, there's no methane. He's throwing the biggest telescopes on the planet at this. The 10-meter KEK telescope, the 4 8-meter VLT telescopes. He's collecting a lot of photons, a lot of light, and he sees no methane. He reports, and you're not going to be able to read these numbers, but that's okay. He reports in his paper that previous observers have reported 3 to 50 parts per billion methane. What are they finding? In January 2006, they report less than 7.8 parts per billion methane. In November 2009, less than 6.6, and in April 2010, less than 7.2. And he says, considering the complexities associated with measuring methane at the low spectral resolutions by all previous observers, those measurements may be affected by instrumental effects and unrecognized solar water signatures that dominate the spectral regions used by these teams to search for methane. And then he gets nice again. He says, if methane is being released into the atmosphere, this process is probably sporadic and not continuous. One of the co-authors of Villanueva's paper was Mike Mumma. I think I know who wrote that sentence. Okay? Just guessing, but all right. So does Mars have methane or doesn't Mars have methane in the atmosphere? That's still the question. And we haven't given up looking, but now we're sniffing really hard up and close. We dropped the Mars Curiosity rover onto Mars in 2012. This is the best selfie ever taken. Okay? The camera is up here, and it just moved the camera all over the place and took lots of pictures. And it's about 2,000 different images of itself that NASA folks put together to create that selfie. It's pretty cool. All right, so the Curiosity rover landed on the surface of Mars. The Curiosity rover is a chemistry laboratory. It's a roving chemistry laboratory that we have sent to Mars. And it has a little sniffer, a couple feet off the ground. And it sucks in Mars air and puts it into the chemistry facility and tests the air for stuff. It does lots of other stuff besides sniff the air, but one of its jobs is to sniff the Martian air. And one of its most important jobs is to try to detect methane in the Martian atmosphere. The Curiosity rover is not looking through the Earth's atmosphere. It's not looking through Mars's atmosphere. You don't have to make any of those corrections. You just have to sniff and measure it. This we can do, and it's a very, very, very sensitive detector. December 2013, they reported their first results. No methane. They actually reported a number less than 0.2 parts per billion methane. It's not much methane if there's methane there. It's not 4, it's not 8, it's not 10, it's not 60, it's not 250, 0.2. That was a big, big result in December 2013. This effectively put the kibosh on there being any detectable methane in the Mars atmosphere. But wait. December 2015, 2 years later, the exact same team reported that they had detected methane at a level of 7 parts per billion. That's a pretty big number. When you are accurate in your measurements to a level of 0.2 parts per billion, 7 is easy. If you're measuring 7, 7's there. And in fact, there is not a single person on this planet, at least, I don't know about the Martians, but there's not a single person on this planet who questions the accuracy of that measurement. If they measured 7 parts per billion methane, there were 7 parts per billion methane in their instrument at the time. No one's debating that. The interesting thing is the methane wasn't there all the time. From when Curiosity landed until through November of 2013, there was no methane detected. And then in December of 2013 through early February of 2014, Mars hiccuped. And there was methane at about this level, 7 parts per billion. And then the methane went away again. Yes?
Did it move around during that time? Could it have been a
Oh, it moved about as far as the footprint of the spacecraft. The Curiosity rover is a rover. It has moved 1 kilometer in 6 years. It hasn't gone far. So if the methane was produced on this part of Mars, did rover run away from it to another part of Mars? No. Could a bubble of methane have just floated over the rover and gone on by? Possible.
There's somebody up there, they're messing with us.
They're messing with us, all right? Somebody's messing with us. Okay? All right, so during this 2-month period from December 2013 to February 2014, the rover detected methane. Before that, no methane. After that, no methane. But they detected methane. So you know what's coming here, sort of? The headlines. The Guardian in England. Curiosity rover's discovery of methane spikes. This is of methane spikes. Fuels speculation of life on Mars. The BBC reports methane gas clue to life on Mars. The New York Times, a great moment. Rover finds methane, a clue that Mars may harbor life. The New York Daily News, theory of life on Mars get an impetus with discovery of methane. And National Geographic, alien life on Mars? Rover spots methane, a possible sign of microbes. Methane is a possible sign of life on Mars. That idea hasn't gone away. So what have they found? Carl Sagan said something important. Extraordinary claims require extraordinary evidence. Most of you have heard this statement from Sagan before, and this is an extraordinary claim. The detection of methane by the Curiosity rover is an extraordinary claim. What does it mean? Folks have done a lot of homework trying to figure out how you could produce that amount of methane on Mars. So here are some possible causes. A busy slide. Start in the top left. Cosmic dust. Dust from comets and asteroids rain down onto the surface of planets. The Earth collects tons and tons of meteoritic dust every day. And Mars does as well. This cosmic dust is carbon rich. It rains down onto the surface. Ultraviolet light penetrates Mars's atmosphere because Mars has no ozone layer to protect it from ultraviolet light or to protect colonists on Mars from ultraviolet light. The ultraviolet light gets to the surface. It interacts with that cosmic dust that produces methane. That could produce 10 parts per billion methane. If that process is at work on Mars, it shouldn't just work in Martian winter or summer. It shouldn't be seasonal. It shouldn't be a function of latitude and longitude. But that process that produces dust all over Mars and ultraviolet light hitting the surface of Mars everywhere could produce a few, maybe 10 parts per billion methane. And again, that methane would then get destroyed, but it would be recreated by more ultraviolet light and more cosmic dust. Top right, we have another method. We have in the soil, possibly, formaldehyde and methanol. Winds from the Martian atmosphere stir this stuff up. It interacts with the carbon dioxide, and it produces methane. Maybe. This particular model for producing methane hasn't been tested anywhere. It's a theoretical model. The folks who put it forward think it's a good idea. Maybe it'll work. Maybe it could produce a little bit of methane. Bottom right, olivine rocks, which are abundant on Mars and are abundant on Earth. Olivine rocks below the soil, below the surface, interact with water. We know there's water. We know there's olivine. They produce methane. The methane then bubbles out of the ground, and maybe you could even get hiccups of methane as the methane accumulates in subsurface bubbles, and something happens to cause that bubble to erupt through the surface. You could certainly produce 10 parts per billion methane from serpentinization, as it would be called. And then we have a fourth method, and those would be the microbes. If there are methanogenic bacteria beneath the surface of Mars, they could produce our 10 parts per billion methane. Yes?
The one over here on the right, when we talk about, little earth, when we have earthquakes, is it releasing any kind of methane? Is that
Methane is released during earthquakes from some places, I think. But most of this methane on Earth doesn't require earthquakes to come out because the Earth is constantly stretching and cracking, and the methane can bubble out.
But I'm just saying, could there be something similar to that on Mars?
There could be. And we are about to land a spacecraft on Mars that's going to listen for Marsquakes. So we may, in fact, find out whether Mars has the equivalent of earthquakes that could split the surface and bubble this stuff out. So 4 different methods for possibly producing this methane. So we had a report in a journal called Geochemical Perspectives Letters that says there could be a cometary origin for the Martian atmospheric methane. Geophysical Research Letters had a paper talking about the serpentinization, have olivine will gas, serpentinization and the abiogenic production of methane on Mars. But there's actually one other possible source of methane, and that is the rover. The rover may have detected methane that they brought from Florida. Okay? This might be the most expensive experiment ever to prove that life exists on Earth. Okay? Okay. Did Curiosity detect methane on Mars or just its own exhaust? Kevin Zonley is a very good planetary scientist. I am convinced that they really are seeing methane, but I'm thinking that it has to be coming from the rover. All the little hoses, all the tubes inside this device came from Earth. And they sat on a launch pad in Florida for a long time, soaking up the methane. They may have detected Florida methane. We need a recount. All right. But this isn't over. All right? January 2018, just a few months ago, in Science magazine, where all this stuff has been reported, a new report on Martian methane from the Curiosity rover. They say now that the background level is not less than 0.2. They're detecting the Martian background level of methane. And there is a background level of about 0.4 parts per billion. That's not the upper limit. That's not the noise. But that's how much methane you just always have in Mars's atmosphere. 0.4 parts per billion. Solid detection. But they're detecting that number varies with the seasons. It can go down to 0.3 parts per billion or up to 0.7 parts per billion measured through 2 Martian years. Why are there seasonal variations? Why are the numbers at that level? They have not detected another hiccup. They have not, since January 2014, they have not detected another hiccup of 7 parts per billion. The numbers have gone as high as 0.7, 10 times lower. 0.7. Is there a deep underground source of methane? Are there meteorite showers? Do you get these high levels of methane every time Mars passes through the tail of a comet? That would be the meteorite showers. Or is there biology? Again, people are talking about the biology below the surface of Mars maybe producing 0.7 parts per billion methane. That bacteria stuff, the methanogenic bacteria, we're supposed to be producing 250 or 30 or 10 or 29 or... We're now down at this level, but we're also, we still have this hiccup from 2014 when it went up to 0.7 for 2 months. But remember, the lifetime of methane in Mars's atmosphere is about 300 years. Those 7 parts per billion should take 300 years to disappear. They didn't. They took a month to disappear. Which means if it's real, it was not a global layer of methane. It was a little cloud of methane that hiccuped out of the ground, a localized source, that then floated over the rover. The rover detected it, and then it floated on by and dispersed, and now it's undetectable. And maybe those hiccups don't happen very often. And this is incredibly hard to test. But the bottom line from all of this methane stuff, and you add in, with a skeptical approach, the Viking results, and you add in, with a bit of skepticism, the Martian meteorite results, and you cannot dismiss the possibility that there could be living things, probably, if anything, methanogenic bacteria, below the surface of Mars. We cannot say that Mars is sterile. There are no giraffes and zebras and worms on the surface of Mars. There are no Martian engineers. But there could be life below the surface of Mars, deep underground. We've drilled deep underground in the Earth, and we find life deep underground in the Earth. If life formed on Mars a long time ago, it could be hiding down there. It could be there. And we really don't know. That's where we are right now. The evidence can't be dismissed. Okay? So the jury is still out in deciding what the answer is for life on Mars. So I want to take you, last thing we're going to talk about, because I have a few more minutes, I want to take you somewhere else in the solar system. This is Europa. Europa is a moon of Jupiter. Europa is a very warm moon, not because it's close to the sun, but because the tidal pull of Jupiter stretches the moons of Jupiter, and stretching a moon is like squeezing a tennis ball. It pumps heat into the moon. So Europa is warm enough that it is soft. It is so soft you don't see any craters on the surface. They're just, and that might be a crater there. But the surface is smooth. It's polished because the surface is too soft to hold a crater. And craters accumulate quick enough in the solar system that we know Europa's surface effectively is a young surface. Local activity has smoothed out the surface. What is going on with Europa? Europa is about half water and half rock. And it is warm enough that it is soft enough that the rock, which is dense, has settled to the center, and that's forced the lighter water to bubble up to the surface. Europa has a surface of water ice. It's just water ice. Just like on the Earth, if you go to Mammoth Cave, as you go down, it gets warmer. Inside a planet, it gets warmer. So as you go down through that layer of surface ice, eventually the water gets warm enough that it becomes liquid. Planetary scientists are 100% convinced, no disagreement on this, that this is the structure of Europa. It has a rocky core. Surrounding the rocky core, there is a global liquid water ocean. And on the surface is a global layer of ice. The layer of ice might be 10 or 20 or 100 kilometers thick, but the ice goes halfway down to the center of Europa. It goes 1,000 kilometers down, and eventually that water ice turns into liquid water. Inside Europa, you have everything you need for life. You have liquid water, an ocean. You have calcium and carbon and phosphorus and magnesium and oxygen and zinc and all the elements that make up the rocky part of the Earth. Europa has that same stuff too. You don't have sunlight penetrating into that ocean, but we have found lots of places deep in our oceans, at the deep trenches, where there is life that does not depend on sunlight. It's DNA-based life on Earth, but it has nothing to do with sunlight. It doesn't do photosynthesis. It gets its energy from chemicals at the bottom of the ocean. Europa could have life. Europa has these geysers that are erupting from the surface, water ice geysers that we've measured. So in principle, we could collect some of that water and see what's below the surface. Another place, Enceladus. Enceladus is a moon of Saturn. Enceladus also is very smooth. It's got a few craters up here, but it's a very smooth surface with all these cracks. Its internal structure is just like Europa's. It has these water ice geysers that erupt hundreds of kilometers into space. Got one more. This one's the best one. We could fly something, fly a drone through that, collect the water, see if there's life below the surface of Enceladus. So let me tell you about what we have done with Europa and Enceladus. NASA had a mission that orbited Jupiter from about 1995 to 2003, the Galileo, 1989 to 2003, something like that. When the mission was running out of fuel, the planetary science community unanimously agreed that we should not take the risk of allowing that spacecraft to crash into Europa, because Europa could have life. Once it's out of fuel, we can't control it. It's just orbiting Jupiter, and it might crash into one of the other moons, or it might crash into Europa, or it might never crash. It might crash next week, or it might crash in 10 million years. We're not going to risk it. So they used the last little bit of fuel to steer the spacecraft into Jupiter and have it burn up in Jupiter's atmosphere so that it could never crash into Europa, and that we would not risk contaminating Europa. We had a space mission, the Cassini mission, that was in orbit around Saturn. Studied Enceladus, took these pictures of Enceladus. And in September 2017, after 14 years of studying Saturn, the Cassini mission was running out of fuel. What did we do? We're not going to contaminate Enceladus. The last little bit of fuel in Enceladus was used to steer it into Saturn's atmosphere and burn it up so we could never contaminate Enceladus, because life might exist below the surface of Enceladus. Mars? We're going to send colonists to Mars? When we're spending all this effort trying to figure out if life could exist on Mars? Because Mars is the most likely place in the solar system where life might exist, and we're looking for it? Now, we do have rovers on the surface that are contaminating Mars in a minor way already, but probably not in a significant way. They're not drilling down deep into Mars. Okay, this 2000 InSight mission is on its way to Mars. It will land on Mars Monday after Thanksgiving, in 3 weeks, November 26th. Its mission is to look for Marsquakes, among other things. Its mission is to study the inside of Mars. That's why it's got that name, InSight. In 2020, we'll launch another rover, the ExoMars rover. The ExoMars rover's task is to look for evidence of life on Mars and find some rocks that might provide that evidence and put them in a storage cache for a future spacecraft to go and grab the rocks and bring them back to Earth for us to study. There are a lot of people who really think Mars could have life. But we're not treating Mars the way we have treated Europa and Enceladus, in saying hands off. That, to me, is a very interesting ethical difference in how we're handling this. My personal feeling is we ought to have a timeout. We ought to spend enough time investigating Mars robotically with these little robots without humans, because without humans, we run very little risk or a minimal risk of contaminating Mars. We could study Mars for another few decades until we are 99.99% certain that Mars is sterile or that Mars has life. And if Mars is sterile, then who cares? Let's go colonize Mars. If Mars has life, then we ought to be having a global discussion about whether we have the right to contaminate Mars. Because if we contaminate Mars and Mars has pre-existing biology, I think the Martians lose. Okay? We know how that has worked on Earth. Martian life probably won't survive us contaminating Mars. Right. I have a link here that I just published if you want to play with this. This is, I don't know how to link it. This is from what's called The Conversation, which it's here on my screen. It's not there. Anyway, you can Google The Conversation and Mars and Weintraub when you find this article. The article is about whether we should be contaminating Mars. It's sort of a follow-up to what we're doing. It was published November 6th, so just last week. So I'm done. Thank you very much for being here, for listening. Thanks.
I just wondered if the relative indifference is because we as human beings aren't as concerned because we don't think it's anything like that.
Could the relative indifference about Mars be because we're not concerned? I have talked to certainly a number of people who say, who cares? It's bacteria. A very substantial amount of your body weight and my body weight is bacteria, right? We can't live without them. We can't live with some of them, but can't live without some of the others. You know, bacteria is fundamental to life on Earth. But yeah, if they don't look like us, if they're not Martian engineers, do we really care? And there are plenty of people who would say, no. If they're just bacteria, and certainly there's nothing on Mars other than bacteria at this point. And if it's just bacteria, we should just take over the planet. That's what a lot of folks would say.
But if they brought it back and it infected us with a terrible disease, that would be kind of ironic, wouldn't it?
If they brought it back and infected us and wiped us out, it would be ironic to the few who survived that. Yeah. Yes, sir.
Our nearest neighbor is our own moon. Did
Yes.
we early on determine there's nothing?
Our nearest neighbor is our own moon. Yeah, we've determined there's nothing there. The Earth has, the moon has no atmosphere. The moon has no water other than a little bit that's hiding in craters near the poles that have been deposited there by comets. No pre-existing water. No water below the surface. It has no atmosphere. The moon's sterile. We're 100% certain of that. So we should go colonize the moon, except it's hard because there's no water. There's no atmosphere. Yes.
I guess I want you just to expand a little bit on that moral issue about.
Expand on the moral issue. Do we have the right to take the risk of destroying a pre-existing biology on another world? Okay. I don't think we do. I think if life got started on Mars, Mars is for the Martians. But let me also give you a scientific question that has nothing to do with the morality of it, and that is, I just want to know if there's life on Mars. If Mars is the closest place in the entire universe where life could exist, if we make these observations and find out there is no life on Mars, that goes a long way to telling us that life in the universe is hard. Life might be very rare in the universe. But if we detect life on Mars, then the life either is DNA-based or is not DNA-based. If it's DNA-based, it didn't arise separately on the two different planets. Life arose probably on Mars, and a rock hit Mars, knocked an asteroid to Earth, and seeded the Earth, which means panspermia, the idea that biology can travel from one world to the other, actually works. That would be enormous to understand scientifically. And if Mars has biology that is not DNA-based, then we know life got started independently on two different planets around the same star, and that probably tells you life is easy, and that probably tells you life is abundant in the universe. The scientific answers from finding out are enormous. If we discover life on Mars and it's DNA-based, but we've already contaminated Mars, there are substantial difficulties in then deciding whether the DNA-based life on Mars is independent of DNA-based life on Earth. We'll have ruined our chances to learn that answer to that question. So there are scientific questions which I think are very important, but they're not really the moral ethical issues. The moral ethical issues, I think, are as simple as the question, do we have the right to take the risk of wiping out the Martians? We wiped out the dodo birds. We wiped out most Native Americans. We are pretty good at wiping out native species when we humans take our culture, our waste, to another part of this planet. So if we take it to Mars, the chances are pretty good we will wipe out the Martians. There's also a risk we'll bring back Martians to Earth, and they could wipe out us. So I think we ought to understand both of those risks before we take either one on.
Silicon has many properties in common with carbon. And there are some theories about silicon-based life.
Silicon has many properties in common with carbon, so there's been lots of speculation, especially in science fiction, that you could have silicon-based life. Our computers are effectively silicon-based life, if you will. I think most biologists have, at this point, dismissed silicon as a real good counter to carbon as the building block element for life, because it actually is not nearly as versatile. It has lots of problems compared with carbon. Most notably, when silicon grabs an oxygen atom, it doesn't let go. Silicon chemistry is actually very hard because it won't let go of that oxygen once you get the silicon-oxygen bond. Whereas a carbon-oxygen bond, with a little bit of energy, you can break that apart and you can do chemistry. So silicon's got some problems, but that doesn't mean we can dismiss it completely. Last question?
Is there a world organization that governs all of these things, like who gets to land on Mars?
Is there a world organization that governs who gets to land on Mars? No. If you have the wherewithal to build a rocket and get to Mars, you can go. Okay? That's what Elon Musk is doing. That's what Jeff Bezos is doing. That's what, Virgin Air wants to do. I mean, if you've got enough billions of dollars, no, there's no organization to stop you. Now, it costs a lot of billions of dollars, so not everybody can just do this. And yes, the United States government has a voice in saying to Elon Musk, you shouldn't go, or you should go, or why don't you work with us to go? But we can't stop him. We can't stop anybody who wants to go. Sort of James Bond goes to space. If you want to do it, you go. All right. Thank you very much. I've enjoyed it.